All right. So today we're going to be talking about 6.4 from Module 6, and they're gonna introduce some new ideas. Now, last week we first got introduced to the idea of similar figures, um, and here we're going to see that we can create similar figures by using parallel lines that are cut by transversals. So in the case here that it's in this picture here, what they're showing us is there's two parallel lines here, and they are cut by two transversals that themselves intersect up here at some point A. And if you look at it carefully and you think about it, you might realize that there are two triangles there. Can you see the two triangles in the figure? There's one triangle right here. There's another triangle right here. And those two triangles are similar figures. So here it says, draw two intersecting transversals on a sheet of line paper as in the following diagram. We got it right here. Label the point of intersection of the transversals A. There A is labeled. Select any two horizontal lines and form the third side of two different triangles. So when they say horizontal, they mean that these two lines, they want both of these lines, since they're horizontal, they need to be parallel. So there's some other additional labeling that I can put in here to help me. For instance, where each of these horizontal lines, where they intersect the transversals, we could actually put a vertex and label them B and C and D and E. So we can label those points. And this first question says, what convinces you that the two triangles formed by the transversals and the horizontal lines are similar? What they're saying here is they're saying that triangle ABC is similar to triangle ADE. So triangle ABC is this little triangle on the top, triangle ABC. Triangle ADE, triangle ADE is similar. And notice the similar symbol is, it's just a little tilde here. In fact, I don't think that line's supposed to be there. It's just the little tilde symbol, little squiggly line. That's what means similar. So what convinces me? Well, I'm able to make some observations about some of the angles here. For instance, this angle, which I could call angle B, and this angle, which I could call angle D, those two angles are equal to each other. What lets me say that those two angles are equal to each other? Can anybody tell me what is the property of angles that lets me say these two angles are equal to each other? Think about those different types of angles that are out there. Alternate interior, alternate exterior, same side interior, alternate interior. I already said that. Corresponding angles. These two angles, I can say that angle B is congruent to angle D, and for the same reason, I can also say angle C is congruent to angle E. So I could put this in with a little angle symbol and double tick marks to show that these two angles are equal. Why? Why is this true? What's the justification? Does anybody know what type of angles these are? Which is why they are congruent to each other. These are a certain type of angle here. They're not vertical. Vertical would be across of each other. So like if it was across these two cross lines right here, above and below here, those are vertical. Those are vertical. These two would be vertical, so not vertical. And for sure, it does not going to involve interior, is it? Here's the parallel lines, and two of those angles are definitely not on the interior, are they? So it's not going to involve interior. They are corresponding, yes. These two are corresponding angles. Aren't they in the same relative position, relative to the parallel lines? The transversal cuts them. These are corresponding angles. Same thing. Angle C and angle D. They are also corresponding angles. Brings me back to, not Chicago, but brings me back to this one right here, man. This is one of your guides that helps you. You know, you see, we got two horizontal lines, don't we? And then I have two angles in these positions right here. And they are 2 and 6, 6 and 2, they're corresponding angles. These notes right here, this is your guide. Put that back over there and we continue here. So the reason why is they are corresponding angles. Now question 2 says label the vertices in the triangles, write some proportionality statements about the sides of the triangles, and then verify the proportionality statements by measuring the sides of the triangles. So some of the statements that I came up with were that the side AB is proportional to the side AD. So AB is proportional to AD. And it'll be equal to, if I go down a different path here, BC to DE. That's one proportion that I could write. Another proportion that I could write is I could write that AC, so that's going here, AC is to AE, that will be proportional to AB divided by AD. Basically saying the ratio of this line, the ratio that's made by the length of this line divided by the length of that line is going to be equal to the ratio of this line divided by that line. If these are similar figures, those ratios are always going to have to be equal. Similarly, AC over AE, that's AC divided by AE. This ratio would be also equivalent to AB divided by AD. Now, you could, if you don't get the idea here, you could like start thinking you can just pick any old letters and it's going to be okay. And there's a pattern here. Let me show you one more of these. AC is to AE, and it's going to be congruent to BC over DE. In all of these cases, do you notice here how I set up short side divided by long side congruent to short side divided by long side? AB short side divided by AD long side. BC short side divided by DE long side. Get the idea? Short side divided by long side. You could also flip it around. You could do long side divided by short side too. All of these could be flipped over. I could say DAD divided by AB is congruent to DE divided by BC. I could flip all those over and I'm still going to get congruent ratios. Now this last part says here, select a third horizontal line segment to form a third triangle that is similar to the other two. Write some additional proportionality statements. Verify them with measurements. Notice I'm skipping the whole part about verifying with measurements. I'm skipping that part, but I won't skip it entirely. I'm planning on doing it shortly here, but not on this first example. So let's see. If I picked that horizontal line right there, and I put in a point F and a point G, and got out my trusty dusty ruler, which I've misplaced only for a moment, and then the moment's gone. So now I've got a third horizontal line here. Notice something I get for free, that angle F will be equal to angle D and equal to angle B. Angle G will be equal to angle E and be equal to angle C. Because all I've done is just cut that transversal by another parallel line. So here we are, more corresponding angles. And I could say here that AB is to AF. AB divided by AF would be congruent to BC divided by FG. Slow down, Booth. Hold on. AB, short side, divided by long side, AF. Back this up. Short side, BC. Yeah, short side. BC is the short side. Long side. Yep. Okay, yeah, FG. It's okay. Don't trip. And another proportion that I could write would be AE, so A to E is proportional to A to G. And that will be congruent to AD divided by AF. Now I could get in here with my ruler and I could measure these to the nearest millimeter, but I'm going to save that for the next example. Let me go ahead and make a screenshot of this. Where to put it? Right there. All right, so turn to the page here. 21. Tristan has written a proportion. He's written BD is proportional to AB, and that is going to be equal to CE divided by AC. Now, look at it and think about it. What Tristan wrote, BD is this segment right here. He's saying BD, that segment, that length, divided by AB, which is this length right here, but that ratio will be equal to CE, which is this length between these 2 points, divided by AC, which is the length between A to C. Now, in this case, this isn't actually an entire side of the triangle, is it? BD and CE, both BD and CE, they are just a part of, well, they're a part of this triangle right here. They're also, yeah, but yeah, they are. But they're also part of this triangle right up here. But this is the space that's in between. So the question is, Tristan wrote this down, and Tia looks at it, and Tia thinks that Tristan made a mistake, that it's not right. Because some of the segments of this proportion are not the sides of triangles. He's trying to use these segments right here, which are not actually sides of any of the triangles. But he's using their values in these proportions. And it turns out that Tristan is actually right. He got lucky. Funny how math worked out that way. But it turns out that Tia is wrong. Tia is wrong. Proportion of corresponding segments even the proportion of corresponding segments are equal. So I'm going to do a measurement here. I'm going to suppose that DF is proportional to BD. I want to see if it's true. And EG over CE. But I'm gonna get some numbers on this. So let's see. DF. If I measure DF, take my glasses off and get in here real close. If I measure DF, it's looking to be about 9 millimeters. If I measure BD, that's looking to be 18 millimeters. And I also lined up CE and EG. CE I'm measuring 20 millimeters, and EG 10 millimeters. And I used millimeters because millimeters is a very nice small unit of measure. Are you guys familiar with the millimeters on the ruler? Millimeters are a very nice small unit of measure. So it lets me get some relatively good precision here. So notice here, DF over BD. DF would be 9 over BD, which is 18. And I wonder, does that equal, let's see, EG, which is 10, all over CE, which is 20. And what I should notice here is that 9 over 18 reduces to 1/2 and is indeed equal to 10 over 20, which also reduces to 1/2. This common ratio is 1/2. I also just found the scale factor, BTW. To go from the small side, or the large size to the small side, you would multiply by 1/2. To go from the small side to the large size, you have to flip everything over and you would multiply by 2. And so I'm going to say, based on my examples, what do I think Tristan or Tia is correct? Both are correct. Both of them are correct. Tia's idea is correct. Tristan's idea is correct. Then they did a little extra math down here. They showed some interesting stuff here. I'm not going to go into it. Let me get a copy of this. Now, those are the 2 pages of the exploration. We're done with the exploration. I'm going to do some of the ready, set, go problems. Your assignment is to do all of the ones that I don't do. So I'm going to start on these. In the ready, set, go, up in the top of my paper here, in the ready, set, go, I'm going to put that Pythagorean theorem. The Pythagorean theorem, because we're going to need that for these first 4 problems. For these first 4 problems, they're giving us right triangles. They're giving us 1, 2, 3, 4 right triangles. And in each case, something is missing. Hypotenuse missing. Leg missing. Leg missing. Leg missing. So here I've got a leg missing. This is the one that I'm going to do. I'm going to do number 2. First, I want to write the Pythagorean theorem down. So the Pythagorean theorem states given a right triangle, A, B, and C, C is equal to the hypotenuse, B is leg 2, and A is leg 1. Given this right triangle, where A is a leg and B is a leg, what do you notice connects the legs? What is like the hips that connects the legs of a triangle? Can you see the little symbol that connects the legs? It's that little right angle symbol. The right angle symbol will always connect the legs to each other. How do you always identify the hypotenuse? The hypotenuse is always the longest side. It's also always opposite. The hypotenuse will always be opposite. You know, the little right angle marker, it's kind of got a point on it, and that point is pointing towards the hypotenuse. However you get it in your head so you can understand the anatomy, the parts of a right triangle. So if all this is true, we've got a squared plus b squared is equal to c squared. That's the Pythagorean theorem. Given a right triangle with sides a and b and hypotenuse c, the sum of the square of the sides is equal to the square of the hypotenuse. So problem number 2 right here. I know a leg right here. I can say that equals B, that equals A, and I'll let that be equal to C. C is always the hypotenuse. Now be careful. A squared plus 3 squared is equal to square root of 10 squared. Here's where things could go wrong. In a couple of problems, one in particular, down here, number 4. Number 4, you're going to square the square root of 27. Well, look what I did right here. I'm squaring the square root of 10. What do I get when I square the square root of 10? What's the opposite of addition? Subtraction. If I did 5, take away 5, what do I get? 0, because, you know, it's opposite. What's the opposite of squaring? Square rooting. So if you you square a square root, the square will cancel the square root, and all you're going to get is 10 out of here. Now, I could write this out this way to try to get you guys to see it. If I've got the square root of m squared, this is equal to square root of m times square root of n. Equal to square root of m times square root of n. So I've got this product of square roots. Well, this is equal to the square root of m times m, which is the square root of m squared. And what is the square root of m squared? Just m. Now, instead of an m, put a 10 in there. Instead of a 10, put a 27 in there. If it's 10 right here, what's going to come out? 10. If it's a 27 right there, and it's in a square root that we're squaring, you know, this is all the theory behind it all, but I'm just going to get the number out. Let's see, degree. Picking boxes here, and ooh, I'm not picking the bucket. So I've got a squared plus 9 is equal to 10. I'm going to subtract 9 from both sides. A squared is equal to 1. A is equal to 1. What number squared equals 1? There's only one number that's squared that equals 1. 1 squared. So A equals 1. I found the length of A. You'll do something similar with different numbers on 1, 3, and 4. Any questions about that problem? Breaker. All right. Next, I'm going to do number 5. Create a proportion for each set of similar triangles, then solve the proportion. So they're telling us that these two triangles are similar. In problem 5 and problem 6, they're similar. We know they're similar. That's what we're told. So I know that the ratios of the corresponding sides will have to be equal to each other. So the long side over here is C. I can set C proportional to the long side over here, which is square root of 29. And then over here, I'll have the 15. This long leg will be proportional to that 5. And so C will be equal to 3 times the square root of 29. Now, the square root of 29 is not a pretty number. The square root of 29 is not a pretty number. Thanks there, Fatima. Where did the 3 come from? 15 divided by 5. That would give me 3, wouldn't it? How about this? It was the square root of 29 over here. How did it magically appear over there? Well, I multiplied both sides by the square root of 29. If I multiply this side over here by the square root of 29, the square root of 29's cancel. Multiply this side by square root of 29, got to multiply this side by the square root of 29. So I get the square root of 29 times 15 divided by 5, 3. And there's what C equals. I'll leave it written just like that because it won't get any more exact than that. That's the most exact answer. I'm going to get there on that one. You'll do something similar, but without square roots on problem 6. Let me shoot a picture of this top part. Now we get to these fun diagrams. Try not to be overwhelmed by these. I know that they look a little on the crazy side. That always seems to make it want to focus for me. So they're asking us here for questions 7 and 8, write 3 equal ratios. That's all. They don't give us any actual measurements, so there's really like no numerical answer. But they want us to write 3 equal ratios. And they're just giving us these various side segment lengths of these. And these 3 lines are parallel, and they're cut by these 2 transversals. So let's see here. The short side divided by the long side, AB, would be equal to the short side D divided by the long side C. So I put that first one together. The short side A divided by the long side B, the short side D divided by the long side C, right here, there's one. Another one that would be kind of easy. Just flip these over. The long side B divided by the short side A would be proportional to the long side C divided by the short side D. And lastly, I could write it like this. A plus B divided by B is equal to D plus C divided by, what should I divide by? I divided by B. What should I divide here on this one? What thinketh you? That's right, C. And there's a third proportion. You're writing something similar to these on problem 8. Problem 9 and 10, we just use them to solve. Now we're given numbers here. We're given numbers here, and we just have to extract the information we want. And I'm going to put K right there in the denominator. K is to 2 as 8 is to 3. Long side divided by short side, long side divided by short side. I got these from the same side, got those from the same side. Should work. K is equal to 16 divided by 3. K is equal to 5 1/3. I've got one more problem that I'm going to do, and then I'm done for today. Problem number 9 is pretty much just as easy as what you saw me do here on problem number 10. I sure hope you guys are going to use the time I give you to do something meaningful. There goes Vazzy. Right. So, just to wrap up the go part here, these are some problems that involve slope. You remember slope from back in the day? Slope. It's something you're going to need to always have in your memory especially when you get to Math 3. Besides getting you ready for your final exam, I also need to make sure that I keep you practicing ideas that are going to be important when you get to Math 3. So you can see them, practice them throughout the year, and refresh your memory on this. So it says here, each line below has several triangles that can be used to determine slope. Draw in 3 slope-defining triangles of different sizes for each line, and then create the ratio of rise to run for each. Now, the best way to make this work is to look carefully at the graph. Can I zoom in on this a little bit, please? I know I can. Yeah, much nicer. All right, you go away for the moment. All right. So notice something about this line. I want to put some vertices in, and I'm not just picking any old place to put these. What's so special about these places where I'm putting all these points? Can anybody tell me what's special about all of those 1, 2, 3, 4, 5, 6 points I just put in there? What's so special about them? Yeah, the lines go through them. An X line goes right through a Y line, doesn't it? It's right where an X line and a Y line cross, isn't it? So, first things, identify those points where there is a nice clean X and Y. And then, the way I did it, and I'm kind of happy with the way I did it, I started right here, and I made a triangle with a run of 2 and a rise of 1. Remember that slope, M equals rise divided by run. Rise is vertical change, run is horizontal change. I can also draw this triangle like this. And in this case, I've got a run of 4 and a rise of 2, don't I? And you know what they say, go big or go home, right? I could draw another triangle right here that goes the whole distance. And in this case, my run is 10 and my rise is 5. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Did it in Mandarin too. 10. And every single time, each of these triangles, what do you notice about all of these slopes? I've got M equal to 1/2, M equal to 2/4, which secretly equals 1/2, and M equals 5/10, which also secretly equals 1/2. So I used the figure to create 3 different slope triangles, and then wrote out the various ratios, simplifying them all. And I can see how my slope is 1/2. So that is a wrap for today for me. Stick a fork in me. I'm done. You have the remaining time in class, and I may change that 40 minutes to 30 minutes tomorrow. Probably going to change 40 to 30 minutes. I didn't think I was going to get done so fast, but I'm pleased. I made progress here. Thank you. There we go.